Hi guys, today we're going to be taking a look at equilibrium a little bit more detail here. In the past we talked about the general concept of equilibrium. We know that if you start with chemicals A and B, according to the collision theory, A and B are going to react as they collide. When these effective collisions are occurring, they hit with the right orientation, the right activation energy, they're going to form C and D. So we know that this isn't going to go indefinitely. As you start running out of reactants, you're going to start running out of collisions. And so that forward reaction that we see here is going to start to slow down. Also, as these quantities begin to increase, they're going to start colliding, and there's going to be some chance that they could go in the opposite direction. And so eventually we reach a point where the collisions between C and D are just as effective as the collisions between A and B. And we call that equilibrium. And so once we reach this equilibrium, if it's a good reaction, hopefully you might see something like this, where most of your reactants have disappeared and turned into the products that you desire. This is going to give us a large K value, which means it's a very effective reaction. Now sometimes we're not so lucky and we get something that might end up like this. So in this case, our K is going to be equal to somewhere around 1. So we're not getting as many products as we would hope to get. So we're spending a lot of money on A and B. We're not getting a full return on our investment because a lot of it is still in solution. So what we want to do is try and improve those quantities of C and D that are being produced. So to do that, we use Le Chatelier's principle, and that's really the goal today, is to look and see how Le Chatelier's principle works. So when it comes to Le Chatelier's principle, what it says is we're going to stress the reaction, and it's going to try and relieve that stress. Basically, it's going to always do the opposite of whatever we do to it. So the ways that we're going to stress the reaction would include concentration, temperature, and pressure if it's a gas. So let's take a look. It's easiest to do some examples here. When it comes to concentration, what we're going to do is we're going to be adding something, or we're going to be taking something away. As long as that something is not a solid, we should see an effect. So if we look at this equation here, we have an increase in the concentration of A. So if I increase the amount of A in solution, I physically pour some more A or pump some more A into the reaction vessel, we would expect to see more effective collisions, more stuff present, more collisions. And so for a brief moment in time, because there's more effective collisions on the reactant side between A and B, we're going to see a shift in our reaction rate. We're going to see it shift what we call to the right. And as this shifts to the right, that means that you are increasing the amount of C and D. And as those amounts increase, if A is colliding with B, we're going to be seeing a slight decrease in the amount of B. So we're creating more of that C and D that we wanted by adding more of A. Like I said, it always does the reaction. If I add A, it's going to try and get rid of it. And the way that it's going to try and get rid of it is by turning it into C and D. That's Le Chatelier's principle for concentration. Now, this particular example is probably not the best way to make more of C because I'm spending more money on A, which isn't my goal here. I want to make more C and D without spending more money. So let's see how else we can manipulate the concentration with this equation. Now, maybe I want C. That's the real goal. That's what I'm going to sell, or that's what I need to use. And so I need to produce this C. Now, rather than buy more A and B, what I could do is remove some D from solution. Now, this reaction says, hey, I like a certain amount of A and B and a certain amount of C and D. You just removed D. So it's going to do everything it can to counteract what I have done. So if I remove D, it's going to try and create more. And the way that it creates more is by combining A with B to form it. So we would see, by removing the D, an increase in C, and we would see a decrease in our reactants as it produced more of my products. So that would be an example of using concentration to a little bit better effect to get what you want. Temperature is going to work the same way if you have an endothermic or an exothermic reaction. So in this case, we're told what happens, or we're asked what happens if you decrease the temperature of an endothermic reaction. So remember, when it's an endothermic reaction, our heat goes on the reactant side, and that's going to be some number of joules or kilojoules or calories, whatever unit is being assigned on the particular worksheet that you have. So if I decrease the temperature, in effect, I'm putting it into a freezer or something like that, or a refrigerator. If I decrease the temperature, I'm basically taking this value and removing it. And so if I remove something from the reactant side, it's going to try and counteract whatever I have done. So we are going to see a shift to the left in this example as it tries to replace it. Remember that the arrow will always point at whatever it's trying to make. So if it's trying to replace that heat that I'm removing, A is going to be increasing as well, and so is B. And while A and B are increasing, we would see C and D decreasing. So in this situation, removing the temperature probably wouldn't be the best idea. A better idea would be to increase the temperature. If I was to increase this quantity, it's going to try and counteract that, and it would shift to the right. So a decrease probably is not the best choice. An increase would be better. And then the last one is probably the toughest, is pressure. Now when it comes to pressure, the idea here is it still wants to counteract whatever I'm doing. But you can't really look to one side or the other and say, I'm adding here or I'm taking away here. Most of the time, the way that we change pressure is by manipulating the volume of your container. So I tried to draw two equally sized containers here, container 1 and container 2. And so the trick is, what we would do is we would look at our equation and look for the gases. That's our key here. We got a gas, we have a gas, we have a gas. And so basically on the left-hand side, I have 1 mole of gas, and because I have a coefficient of 1. Over here, there's 1 mole of each of those, so I have 2 moles. Now, as we think about it, if you were to put 1 mole of gas in a container, you're not going to get very many collisions from that. So it's a fairly low pressure. And over on the right here, we have 2 moles of gas, which is going to give us more collisions with the walls of the container. And so this would be a high pressure. Now remember that the reaction's always going to try and counteract, do the opposite of whatever I do. So let's say that I mix all these gases together. So maybe this reaction is 50-50. So I know when it's done that 50% of it is going to be reactants, 50% of it is going to be products. And so in this reaction vessel, I'm going to put one of my reactants, and I am going to put something like this. So it's not exactly 50-50, but it's close. For our purposes, we can see that we've got equal amounts here. So if I decrease the volume, this just raised the pressure. By decreasing the volume, I raised, sorry about that. The pressure. So right now, I've got 3 moles of gas in here that are creating collisions. And so this reaction said, you raised the pressure. It wants to do the opposite. It wants to try and lower the pressure. So how can it lower the pressure? Well, if it lowers the pressure, it's going to favor this side. That's the side that's going to be low pressure. So it wants the reaction to go in this direction and make this chemical, because what that means is these two are going to combine to form a single dot, right? One of these and one of these will only make one of those. And so we went from 3 molecules in that container to 2. And so we got a drop in pressure. So the key when we are working with pressure is if I raise the pressure, it will shift to the side with less moles. Of gas, because remember, only a gas can create gas pressure. So if I was to increase the volume, I would be lowering the pressure. If it wants to lower the pressure, it's going to shift toward the side with more moles, because this one single atom would then split and form two dots, which is going to give us more pressure. So I hope this helps you guys out, and I'll talk to you later.